In this next section, 7.4, we are looking at nonlinear systems of equations. And by the way, we don't cover 7.3, so you didn't miss it. We skip over it. So with our nonlinear systems, we're going to see that this process is going to be similar to what we've done before with the linear systems. We're just thinking about, rather than just having two lines that are intersecting, we could have a line intersecting with another type of graph. So something like maybe a parabola or a circle or an ellipse. So in this little introduction, I'm just going to start by going through a few different types of equations that we're going to see in the lesson today and what type of graph they produce. So first and foremost, we have our line, which we're familiar with. We may see our line in this standard form, like 2x plus 3y equals 10. The big idea with a line is that it involves both x and y, and they're not being squared. Another way that we might see our line is like the slope-intercept form. Anything that looks like y equals mx plus b will just make a straight line. So we've already done work with systems that involve lines. Today we're going to see that there might be a parabola involved. A parabola involves anything with an x squared. It also might look something like this. Maybe we have something in parentheses, x plus or minus something that would shift the parabola left or right, and the squared is on the outside. So if there's just an x squared, it makes it a parabola. Today we're also going to see circles, and this is something that we didn't get a chance to talk a lot about with not doing the conic project, but we have both x squared and y squared in the formula for a circle. This is actually the standard form for a basic circle that is centered at 0, 0, and it has a radius of 3. And so the number at the end of the equation actually represents the radius squared. We could have a circle that looks something like this. This is cutting off, I think it's supposed to be a 9 right there. Notice that we have parentheses for both the x and the y parts being squared. That just means that the center has been shifted. So this one has a center at -4, +1. It's just like when we shifted the center like for an ellipse, where we take the opposite sign of the number in the parentheses. But still, it's still a circle because it involves both the x squared and y squared. Today we also might see an equation for an ellipse that looks a little different from the standard form equations that we did in Chapter 9. This one here, we could actually transform it into this, what I'm writing here, so that we could actually figure out what the graph is going to look like. The big indicator for an ellipse is that both x and y are being squared, but the two numbers that are in front are different numbers. That's causing these two denominators to be different, meaning that it's going to be slightly wider than it is tall, and that's what makes it look more like an oval shape rather than a perfect circle. If we see both x and y being squared, there's different numbers in front, and we have a subtraction sign, that is going to make a hyperbola. So just like we saw in Chapter 9, the addition causes an ellipse, subtraction makes a hyperbola. So now I've drawn out some possibilities for what it could look like for a nonlinear system. There's other possibilities as well that I haven't shown. These are just a few. So we're going to think about like a line intersecting with a parabola. If it looks something like this, we would actually have two solutions since there's two intersection points. Over here, this line intersecting with a circle also has two solutions. A line could intersect with an ellipse. I like this shape down here. This kind of reminds me of like Saturn, the planet. There's a circle and an ellipse crossing through it, so there's actually 4 intersection points. So we're going to see some problems today that have more than 2 solutions. This one has 4. A circle and a circle would mean 2 solutions, and so on. So those are just some different possibilities of what we're going to be looking at in our nonlinear systems today. We will solve this nonlinear system by substitution. Notice how the top equation is already in the form of y equals. So we can take this entire expression and plug it in for y into the bottom equation, giving us x plus x squared plus 2x plus 1 equals 1. This is the part that we plugged in. Combining like terms gives us x squared plus 3x plus 1 equals 1. And since it's quadratic with the x squared, we must move everything to the one side to get it equal to 0. Once it's equal to 0, the next step is to factor. Here we only have 2 terms, so we can only factor out the greatest common factor. In this case, it will be x. We want to set each factor equal to 0 and solve for x. One solution we get is x equals 0, and the other solution is x equals -3. These are the x values for 2 intersection points. We need to plug those back in to one of our original equations to get the corresponding y values. It will be easiest to plug it into the second equation. If x is 0, y is 1, and if x is -3, y is 4. When we list our answers, we want to make sure that we list them in the order x, y, and that the numbers are corresponding. So this is a visual of what the graph would have looked like for that last problem that we just solved. So we have our parabola intersecting with a line. We can see that the intersection points on the graph are the same as the points we solved for when we did it algebraically. When we were solving this and we found 2 different x values, -3 and 0, we're not done yet. We had to plug them back into the equation to solve for the corresponding y value so that we have all of the information for the 2 solutions that we're going to represent as 2 separate ordered pairs. We will solve this nonlinear system using substitution. To start, we need to rewrite the bottom equation in the form of x equals or y equals. In this case, I will add x to both sides to get y equals 2 plus x. We're going to plug that in for y back into the top equation. X squared, quantity 2 plus x squared, is equal to 10. Now to simplify this out, we must FOIL 2 plus x times 2 plus x. So as a result of our FOIL, we get 4 plus 2x plus 2x, which is 4x, plus x squared. Combining like terms, and we want to subtract 10 from both sides so that it can be equal to 0. So 4 minus 10 is -6. Because there are even numbers for coefficients, we can divide everything on both sides by 2, giving us x squared plus 2x minus 3 still equal to 0. Now we need to factor 2 things that multiply to -3 and add to +2 will be +3 minus 1. Set each factor equal to 0 and solve for x. These represent the x values for the intersection points. Going back to the original, using this y equals 2 plus x, we can plug those x values in to get their corresponding y values. So let's plug in -3 for x. We get y equals -1. So one of our solutions will be -3, -1. When we plug the other answer in, x equals 1, we get y equals 3. 1, 3 will be the other solution. And here's the graph that shows the solution for the last problem that we just solved. So we get the same answer, 1, 3, and -3, -1. So here we can visually see what we just did with the line intersecting the circle. We will use substitution to solve this nonlinear system. We know that y equals 2x plus 1, so we will plug that in for y in the top equation. x times the quantity 2x plus 1 equals 1. Distribute the x and subtract 1 from both sides. Now we need to factor the left. We know that we will have a 2x in front and an x in the other because 2x times x is 2x squared. When we multiply the last terms, we want them to equal -1. So we are going to have +1 and -1. Putting the +1 here makes it so that the outside term is 2x, the inside is -1x, and that will add together to +1x. Set each factor equal to 0 and solve for x. These represent the x values for the intersection points. We will plug them back in to this equation to get the y values. Starting with x equals 1/2, y equals 2, so the point 1/2, 2 is a solution. Plugging in the x value of -1 gives us a y value of -1. So -1, -1 is another solution. So the graph for this one actually involves a graph that we didn't talk about at the beginning in the introduction. The x times y equals 1. As you can see off to the side here, that's really the same thing as y equals 1 divided by x. This is actually the graph of a rational function that we studied back in chapter 2. So it has a vertical asymptote, it has a horizontal asymptote. You can see in the graph here the red shape is that rational function shape, and then we can see the line going through it. We do get the same intersection points that we got by solving it algebraically, -1, -1, and 1/2, 2. We will solve this system by substitution. Let's begin by rewriting the first equation as x equals y plus 3. Now we will take y plus 3 and plug that in for x into the second equation. This gets us an equation in one variable, y. Now we will simplify this equation. We must FOIL 2 times. The first FOIL gives us y squared plus 2y plus 1. Over here we get y squared plus 6y plus 9. Putting like terms together, we get 2y squared plus 8y plus 10. And we want to subtract 4 from both sides to get it equal to 0. 10 minus 4 is 6. Because all of our coefficients, all of our numbers here are even, we can divide everything on both sides by -2, giving us y squared plus 4y plus 3 equals 0. Now we will factor. Find two numbers that multiply to 3 and add to 4. Set each factor equal to 0 and solve for y. These represent the y values for the intersection points. To find the x values, we will go back to this x equals y plus 3. Plugging in the first answer, -3, we get x equals 0. And plugging in the second answer of -1, we get x equals 2. So our solutions are 0, -3, and 2, -1. So here's the graph of that solution. So we have a circle a line intersecting with a circle. So there's our intersection points, 0, -3, and 2, -1. If you look at the equation off to the side here for a circle, we can see that this is one that has the center shifted. The x value of the center is 2, the y value of the center is -3, and the other number represents the radius squared. So if we do the square root of 4, we can see that it has a radius of 2. We will solve this nonlinear system using the elimination method. We can eliminate the x squareds or the y squareds. Since one of the y squareds is already positive and the other is negative, I'm going to multiply the top equation by 3 and the bottom equation by 4. That's going to give us positive 12y squared and negative 12y squared. Now we're ready to do elimination. Adding together 12y squared and negative 12y squared, they eliminate, giving us 17x squared equals 68. Divide both sides by 17 and we get x squared equals 4. When we square root both sides, we get x equals plus or minus 2. We're going to plug in 2 and -2 into one of the original equations. Let's do the top equation. The few steps we need to do to solve. Subtract 12 from both sides. And divide both sides by 4. When we square root both sides, we get plus or minus 1. So that tells us that when x is 2, y could be positive 1, or y could be negative 1. Now, if we plug in the other answer of negative 2, we're going to get the same solution, because negative 2 squared is still going to equal positive 4. So adding to our solution set, we have negative 2, positive 1, and negative 2, negative 1. All right, this last graph is kind of neat. So we have an ellipse being intersected with a hyperbola. So we can see that the ellipse comes from the first equation that has a plus sign. The hyperbola comes from the second equation that has a minus sign. So you can see here the way that they're intersecting. This makes sense why we have all 4 of those solutions.